So next up, have we talked about use cases enough? Never, not yet. So our next panel is going to be talking about the business case for quantum. And we have with us Miss Amanda Stein, who's going to be moderating this panel. So Amanda has been with the university since 2013. She serves as both the Director of External Relations in the Department of Electrical and Computer Engineering and the Quantum Technology Center. In her roles, she leads partnerships and works to translate great research of the ECE and QTC faculty. Prior to joining UMD, Ms. Stein worked in corporate relations for nonprofits, and she did a stint on Capitol Hill. She holds a BA from Florida International University and a Master's of Management from the George Washington University. And if that's not enough, she's also pursuing her PhD through the Information Studies program here at the University of Maryland. So please welcome our next panel, and they will introduce as we come on.
Good morning. I guess I'm the only thing between you and lunch, so we won't make this too long, but thank you, President Pines, for these kind words, and thank you, everybody, for attending. As Julie so nicely introduced me, I am Amanda Stein. I am Director of External Relations in Quantum Technology Center and Applied Research Center here at the University of Maryland, and also Director of External Relations in the Department of Electrical and Computer Engineering. And it's my pleasure today to welcome these three wonderful people to my left. First up is David Coar of Lockheed Martin, and David is a senior research scientist in Lockheed Martin's Advanced Technology Laboratory, where he leads artificial intelligence and signal processing programs, part of the DoD, and with the goal of transitioning technologies out to the warfighter. He has worked in nitrogen vacancy magnetometry, which I actually know what that is now, and he is quite passionate about translation technologies and specifically out of DoD programs. He holds a BS in physics from Clemson University and an MSc in nanotechnology from the University of Pennsylvania. And if one David wasn't enough, we have our second David. Dr. David Hopper is a senior technology analyst at the MITRE Corporation, where he supports MITRE Engenuity, a foundation for public good. He's responsible for determining the commercial potential of MITRE intellectual property, developing commercial strategies, and identifying external technologies that complement MITRE's quantum portfolio. He's the co-author of 10 peer-reviewed papers, and specifically in quantum science, and he also works in nitrogen vacancy diamond centers. David is focused on identifying dual use cases of quantum sensors and solidifying national security. He holds a BS from physics from the Pennsylvania State University and a PhD from physics from the University of Pennsylvania. And if it wasn't enough that they both are named David, they actually both went to the University of Pennsylvania, and they actually knew each other there, which is kind of cool as well. The last person on my panel, Denise, so I guess your name has to start with a D to be on this panel. Denise Ruffner is Vice President of Business Development at IonQ, which we just heard a lot about from President Pines. And she's also president of Women in Quantum, a worldwide organization of over 9,000 people providing a support network and encouraging diversity, specifically in quantum computing. Previously, Denise was Chief Business Development Officer at Cambridge Quantum Computing and was an early employee at IBM Quantum. So it's my privilege to have the three of these wonderful folks on the panel today talking specifically about near-term commercialization opportunities. So this is something that I'm actually personally interested in as well. As Julie mentioned, I'm working on my PhD and looking at the non-technical side of quantum, because while I'm not a physicist, I'm very interested in these commercialization opportunities, the business opportunities, and where quantum's going from this non-technical perspective. So this will be a less technical panel today and a little bit more focused on these near-term commercialization opportunities. So Dave is representing the quantum algorithm space. David is representing more of the quantum sensing space, and Denise representing more of the quantum computing space. So let's start there. Dave, what is quantum algorithms? What does that mean to you?
So at least for us at Lockheed Martin, we kind of break quantum algorithms into three main pillars. How do we apply what we know today with the available hardware to try to create applications for the warfighter? We're also looking downstream what we can do in terms of building better building blocks for quantum algorithms to provide technology that we don't even know about today. And then lastly, like I said, we're a big engineering house. So we're trying to find ways to work with hardware companies to accelerate the design process and system optimization to get capability accelerated, and at least in our case, in the hands of the warfighter faster.
Dave, same question related to quantum sensing.
Yeah, so for quantum sensing, what we really look at are any physical systems that are relying on sort of discrete energy levels to give you information about the environment. And if you're looking at how to build a quantum sensor, you actually need to have a lot of the things that a quantum computer has, except for maybe the hardest part, which is generating large-scale entanglement. That's actually a feature for quantum sensors. You kind of want to lose your entanglement because that tells you about your environment. One good example of that is a recent result from Google where they're actually able to detect cosmic rays hitting their quantum computer because they could find these correlated errors occurring in their system, which actually has some important implications for error correction because correlated errors are sort of tricky to avoid, but that's sort of how quantum sensors come about.
Thank you. So Denise, we hear a lot about quantum computing, and I think that's one of the most near-term applications. But for those of us who don't really know what quantum computers do, what are the exact kind of near-term applications for quantum computers?
So that's still an area of debate. There's a lot of progress being made in what the different applications are. At IonQ, we have a lot of expertise in machine learning, optimization, and chemistry. And those are probably the 3 areas of focus that we have with our customers. And I think what I want to say is I have the great job every day of talking to people who go, what if? Could we do this? Could we do that? And I think that's probably one of the best jobs in the quantum industry is to get together with people that have fabulous ideas and then be able to bring it back to this very talented team with great hardware and see what we can do to help them.
So the conversation, especially related to quantum, has been very much focused on quantum computing. So David, related to quantum sensors, what are some near-term applications related to quantum sensing specifically?
Yeah, so I'll talk about one that I'm working on at MITRE and in close collaboration with UMD and with Amanda. It's been helping out a lot.
Yeah, that question totally wasn't planted.
So this is a project in the semiconductor manufacturing space, particularly the failure analysis of those chips. So the semiconductor industry is really driven by the yields. Can you make enough chips and get them off the line, and can they be functional? Well, when a chip fails, you need to figure out what exactly went wrong. You perform a root cause analysis on that. That is an incredibly hard problem to say, going from a chip scale and maybe 2 pins are failing to, okay, our gate broke down at this specific point when you're at these 2 nanometer, 3 nanometer nodes. So one thing that we found out is that if you could provide a magnetic field image above your semiconductor chip, these failure analysis engineers get really excited about that because then they can start inferring, okay, where's the current going through our chip? Can we use that to figure out what went wrong? And then start going further down to localizing the actual failure. And so we're using diamond nitrogen vacancy centers to build that magnetic field image. So you can basically just put your diamond above a semiconductor chip, and after a little bit of processing, a laser and some microwaves, you can get that magnetic field image out. And so this is something that we talk to people in industry, and they're excited by. They're saying, oh, this is a really interesting tool. They're asking us to sort of push the engineering boundaries of it. And then so we're really taking this quantum sensing technology. It's been developed over probably the last decade for NV centers, and try to really get it into this critical industry for so many different things.
And Dave, you worked a little bit in nitrogen vacancy centers as well. So what other use case applications in that area are you seeing?
Yeah, sure. So we focus primarily on sensing magnetometry for anomaly detection. There's a lot of DoD applications at not the very fine resolution, but more at the bigger scale, exploiting the vector nature of the sensor combined with the high bandwidth. And so those are definitely applications. There's a lot of DoD applications related to what you can do with a sensor like that. And it's very promising.
Wonderful. So let's switch over back to quantum computing for a moment. So clearly companies like IonQ, Rigetti, even Google and IBM are building quantum computers, but you need algorithms and things like that to run. So Dave, back to you. What are you working on as far as quantum algorithms or algorithms to advance in quantum computing space?
Yeah, sure. So right now, like I said, Lockheed is really focused on monitoring the field and trying to become early adopters. So our goal is to partner with folks like you all in the room, have access to hardware, and then help link you guys up with the applications that we can create that pull to create value for our customers.
So Denise, then, from the IonQ perspective, what's kind of the next step with this, working with algorithms, working with maybe companies like Lockheed Martin, working with some of your partners? Where is that going for near-term applications?
So there's different projects, right? So we have many, many different projects going on, and a lot of really good early publications on advances we've made, particularly recently in the finance industry, and the paper out of UMD on error correction. So there's a lot we're doing to move it forward, and looking for that elusive early application where we can show quantum advantage. And we think that's coming, and we're very optimistic about our team and the work we're doing. So I would just say stay tuned, and we hope to have some announcements as we continue to work with our customers.
That's exciting. I mean, you're already seeing out in the news these partners coming out of not just IonQ, but all these quantum computing companies, everything from the automotive space to biopharmaceuticals to medical devices. And then once you tie in quantum sensing and quantum computing, I mean, the possibilities are kind of endless. This question goes out to all of you. If you had to pick maybe one modality, more so the quantum sensing, quantum materials, quantum computing, what do you think, if you had to make your bets right now, what would be kind of first to market?
I can start off. Like I said, I think from the DoD's perspective, I think sensing is probably one of the first to get fielded. Like I said, we've seen a lot of work, not just in NV magnetometry, but in a lot of other quantum-based sensing modalities and timing. There's a lot of really good advances that is going to has the potential to offer a lot of discriminating capability. So I think sensing probably first for at least DoD.
And I bet, David, you probably might agree with that based on what we're working on.
I'd probably agree with sensing as well, and the timing aspect too. I mean, atomic clocks are already ubiquitous and all over the place, and heard some really interesting conversations of, well, what if we can bring atomic clocks, like really reduce the size, weight, and power and cost? And then you can start opening up a lot of interesting applications for not just the DoD, but telecommunications as well. So I think that could be a really interesting first play.
You mentioned just something really interesting about the size, weight, power kind of, I don't want to call it a problem, but it is a big research area that a lot of faculty and even faculty here at the University of Maryland are working on. If we were to kind of reduce size, weight, power, both of sensors and even computing, what do you think some of the possibilities is? And maybe Denise, we'll start with you on the computing side.
So IonQ has a very well-defined roadmap and each subsequent version of our system is decreasing in size. So we're moving towards having a box that could go into a rack in a data center in 2023, which we're very excited about the potential. So that makes quantum computing kind of behind the firewall if a company wants it, as well as our continued relationships with the cloud providers allows kind of the world to access the computer. So we're going to see a lot of instances where defense or companies or countries, that don't let certain types of data leave the country, that are going to want to have a computer within their firewall in their data center, as well as continue to have the cloud access.
And then Dave or David, do you have any thoughts maybe related to the algorithm side or the sensor side related to that?
Yeah, I think for SWaP-C, as we always refer to it, and a word cloud and MITRE would probably have, SWaP-C would be up there. I think a great example there is for GPS-free navigation, which has predominantly been a DoD focus, but now that you start thinking of autonomous vehicles, everything's connected, those things need to know where they are, and if you lose GPS, which does happen, you want to make sure everyone knows where they are, and so you need pretty accurate holdover times so that you can guarantee you know where you are, say you go through a tunnel, and there SWaP-C really matters because there's a clear trend between SWaP-C and basically what timing and location accuracy you can
For
get.
those of us non-physicists out there, because I do know we have some folks who are watching, what is SWaP-C?
SWaP-C is size, weight, and power, and cost.
Cost.
So, you know, if you're building a nuclear submarine, you can afford the most expensive system. If you're building a car that's you're going to sell thousands and thousands of units, you know, you need to drive that cost down. So, while maintaining accuracy.
And at least, I think C is the big one, at least initially for computing. Having more access is going to provide more folks like myself and everyone else access to these computers, which is really going to accelerate the rate of growth and what we can do algorithmically. The more we have the ability to play with real hardware and learn, it's going to provide better feedback for you all. It's going to provide better application results for the industry as a whole.
So Dave, you talked about playing with real hardware and real access. Maybe you can explain to our audience kind of what the current state is for somebody in like Lockheed Martin if you wanted to play on a quantum computer, because a lot of people don't understand that you can't just really access a quantum computer.
Yeah, sure. So Lockheed Martin was an early investor in D-Wave. So we actually have kind of a longer history of access than some other organizations. Obviously, with the new hardware, we want to have access to the fundamentally different computational architecture. But right now, like I said, access is limited, and we're looking every day to try to expand that access.
So Denise, you're Vice President of Business Development with IonQ. I mean, how do you get more access, and is that actually possible at this point?
So access is possible. At IonQ, we allow access either through the cloud or directly through us, and that depends on how much time the customer is using, if they want to reserve time, how do they want to work most efficiently. So there are a lot of different options. They can buy a whole computer. So right now it's an interesting time in the market because customers want to use different models to access. There's not a real single trend that they only want it on the cloud, or they only want it behind their firewall, or they only want it. So what we're trying to do is give the customers a menu of things to choose from so that we can do kind of whatever they want us to do in terms of providing access. And I also want to mention IonQ has a research credits program where researchers, this is academic researchers, can apply to us and get $10,000 in free credits to use our device. So part of what we're trying to do is get people in grad school and professors or whoever, get them to get access to our devices and start playing with it, because we all agree that that's the first step to building algorithms.
And that's what's going to create the next near-term applications, right?
Yeah.
There you go. So we've talked a little bit about some of the challenges, specifically about SWaP-C, which thank you for educating everybody about that. What are some of the other ones that you're seeing out there, maybe both within the sensor market and then with the computing market? Maybe Dave, you want to start?
Like I said, it's very early days. So for Lockheed right now, our big thing is convincing that our funding agencies that the technology is in the right state to start accessing DoD-specific applications, working with them, and we're working with a lot of customers now who interest is definitely growing and trying to build out those strategic relationships on how to work with the community better to help transition technology. That's the big thing for us, is working with our customers and providing the right use cases for them.
Wonderful. David?
Yeah, so I think for sensing, it's a similar problem that quantum computing is having, and that's finding the end users that really know their domain and how to use the tool. And for sensing, it's kind of taking physicists and engineers who build the sensors, but they have no clue what it's getting sold into and getting used for. And on the other end, from the semiconductor example I mentioned earlier, they don't know anything about quantum. They just want to know, can I figure out what's going wrong with my chip, and can it be fast? And so sort of building those connections, that collaboration to really drive the R&D into these sort of other verticals that the people building the tools have no expertise in is going to be really important across any quantum sensor, because there's so many different industries that quantum sensors will make a big impact in. You have to build that expertise, and I think that's a big challenge to make those connections and do that learning.
And so Denise, it's a little bit different than what David just described specifically for computing. What are some of the more challenges, and especially with these near-term applications, that you're seeing?
Challenges. Well, I do want to talk about acquiring customers. I think that's something we're all trying to do, and get new projects and kind of get different viewpoints on what people want to do with these systems. So far, I think we've had a great team doing a lot of work. We have a lot of really interesting projects, and I can say over the 5 years or more that I've been in quantum computing and seen the development of customers, we are starting to get not just the same old corporates, we're starting to get new people looking at quantum, and I find that very positive for the industry overall, that we're not necessarily always dealing with the same customers. There are new customers and new people coming in and starting to realize that they need to invest in this technology now. So that part of kind of our jobs is very exciting. And I'll bet you guys are seeing new customers too. And I think that as we get closer to showing quantum advantage in one application, or as we move forward with progress, ultimately there will be this waterfall of customers that people will finally start getting it, that like they need to invest now and come into this.
Yeah, and I will open to the audience, and we want this to be a discussion. If anyone in the audience has a question, please let us know. But I kind of want to follow up from a more like traditional business schools kind of thing, and having in the process of studying some of this and some of the business use cases, what are some of the value propositions that you're seeing in relation to quantum sensing, quantum computing, and even going into quantum materials, quantum algorithms?
Yeah, sure. So at least on sensing, you're seeing higher sensitivities, you're seeing higher bandwidths, and in a lot of cases, maybe not the C right now, but better swap properties. And C will come with better engineering and product, like more scale. At least on the computing side, the promise is definitely what can't we do today? How can we attack some of these algorithms that right now are just not feasible with our current computation?
Yeah, I think I would just add on the looking for spillover effects. I think there's a really great example with the chip scale atomic clocks that DARPA initially funded for the DoD, and basically reducing the swap C of these precise clocks. And that ended up benefiting the oil and gas surveying business, trying to map out seafloor beds. And more recently, a sort of knock-on effect of that was that Facebook is now developing what they call a time appliance, where in their servers they put an atomic clock with a GNSS timing receiver. Basically, to manage their distributed databases, they need very accurate time synchronization. So now you have chip-scale atomic clocks sitting in Facebook data centers, which now that's a really big market, but that all just kind of trickled down over maybe 10 years of development.
And then Denise, the biggest value proposition right now within quantum computing, when customers come to you, what do they want you to solve?
So as we know, high performance computing is very strong, but in many cases can only provide kind of an estimation of a result. And so people are looking for more precision in results and feel that that precision will bring them to a better understanding of what their problem is or what their issues are, and thereby kind of create a value proposition for moving forward with quantum, and also saving the company money by better understanding, for example, a chemical process, or solving a machine learning problem more quickly. So people have yet not really asked us to translate, like, if I do this, you'll save that. People are still looking at what incremental steps they can take towards a very large problem, with the understanding that as we progress through the problem, there's inherent savings and inherent improvements in how they do things.
Thank you. So being in the DC area, we kind of can't ignore that the government and the DoD specifically is in our backyard. And we heard it yesterday that the government specifically is one of the largest funders of quantum, both on the quantum computing side, but more so even on this quantum sensing side that we're talking about. And specifically, the DoD is putting a lot of money as part of the Defense Authorization Bill and part of the 2018 National Quantum Act. So Dave, from your perspective at Lockheed Martin, being one of the largest, specifically DoD contractors in the world, where do you think the DoD specifically and the government are going with this?
So I think it's going to be continued investments primarily out of your research organizations, your DARPAs, your IARPAs, and service labs, where, like I said, I think you'll see more programs like ACES and Quasar. That money will continue to come, but I think there's going to be an added look to start bringing on additional applications and getting things fielded. So I think You can just see that in all of the funding. Everyone's looking for a win at DARPA. Everyone's looking for a way to transition something out of the lab and into the warfighter's hands. And I think that's where places like where I work out of ATL, we primarily do customer research and development. And we work with DARPA and those organizations all the time. And a big reason what we're trying to do is find partners to work with to provide our core competencies in software engineering, signal processing, control theory, and combine with that application pull to help take some of the technology that you all are developing and help provide access to CRAB and access to transition as well. So that's the big goal that really ends up helping everyone, is when we can get a win for DARPA is a win for everyone in this room, it's a win for the community.
And so for David and Denise, I'm curious from your expertise, how do you see the government fitting in with both the quantum sensing and then into the quantum computing space as well?
Yeah, so I think for quantum sensing, we're hearing a lot of interest. I think there's a lot of people in the government who are quantum curious and want to hear what's going on and just get sort of like a quick spiel about it. But then there's a lot of people who start asking those, okay, well, what's the technology readiness level, the TRL? And they're really thinking of, can we start asking some of these funding agencies to actually put out a call for proposals in this? And I think in quantum sensing especially, people are really excited about that. Another one from DARPA is the quantum apertures with the Rydberg atoms, which is generating a lot of excitement recently. So I think it's similar in that regard.
And in the computing space, how does quantum computing companies work with the government?
So there's a lot of legislation, and as Worley said,
that's where I started my life. There's always a lot of legislation.
Right. Yeah, Worley said we should all have lobbyists, but where's Worley? Is he still here? But there is a lot of increasing interest in the government on quantum computing and developing quantum computing, just as we're seeing it with other governments worldwide. But I'm really excited at the momentum that the US government has in quantum computing and how that's increasing. And I think we're all going to benefit from that.
I agree. But David, you brought up an interesting term, quantum curious. Can you explain what that is exactly in your own words?
Yeah, I mean, it's probably how a lot of us got into this field. You hear about quantum, you hear about the promises and what it could be, and then you want to learn more. You want to, start to understand the science, the technology, when will it be available? And I think as people who work in quantum, I think it's good to be able to communicate to that people that are interested and they want to get the lay of the land. And to Worley's point, to be realistic about it while also being optimistic. I think striking that balance, which he did so well, is a good thing to strive for.
I guess that's kind of how I started. I started out quantum curious, and then they're like, you're going to go work with this. There you go. But so since we're at this quantum investment summit, and we're talking about near-term applications, how are near-term applications going to be funded?
Yeah, I think a lot of initial funding, there's going to be lots of opportunities within the DoD, primarily within contract research and development, that will be really good opportunities to help get some of those, especially sensing applications, and at least provide some of that initial pull on the computation for DoD applications. I think that is definitely an avenue that's not going away anytime soon.
Yeah, so I did a little bit of analysis on the quantum sensing landscape, and it's predominantly funded by government contracts. The SBIRs, the STTRs, they're funding a lot of the US quantum companies, even some of the European ones. A few of them have broken that cycle. Cold Quanta is one, but as Scott Ferris mentioned yesterday, maybe that's because of the emphasis on quantum computing moving forwards. But you look at, say, QNAMI, I think in the EU, they've raised private capital to build a diamond magnetometer. Envision, Xella's talk, which another quantum sensing venture that has private capital. I think we need to find more ways to get more private capital, because SBIRs are useful, but they can only take you so far.
Definitely. And then Denise, specifically related to computing, I mean, clearly there's a lot of investment dollars going into computing. We do see that there are quite a few government grants, SBIRs, STTRs, going into quantum computing. But if somebody was trying to create a quantum computing startup, what are some advice, both from the software side and the hardware side, would you have for them?
So I think one of the things we face in the quantum hardware world is that there are a lot of companies out there that want to do engagements for free or for very little money because they want to get that press release. And I am against that. Let me just say that. I believe that you pay for what you get, and I believe that we have a super talented team and high quality hardware, and that has value. And I think it hurts the rest of the industry when we do stuff for free. So we have a very strong position on getting revenue from engagements and giving our best to those engagements. And so that's something people will pay. There's a lot of business out there for all of us. I'm constantly amazed every day at the new people that I talk to and that are interested in quantum. And I would just say there's a lot of business out there, and there's also revenue out there for each of those engagements. So don't give it away for free.
My mother told me that too. Do we have any questions from the audience? Well then, since we are the last thing between you and lunch, I will wrap it up with one final question. So the IP is big, and lawyers are making a lot of money off of IP. So from the Lockheed Martin perspective, from the MITRE Engenuity perspective, from the IonQ perspective, where is the IP coming from, and how important is that to your specific companies?
Sure. So at least for Lockheed Martin, right now, the primary mechanism that at least we're tracking the space is through investment, so like Lockheed Martin Ventures. So we're participating with small business that way, is the primary access into IP, and just having access to those companies, looking for exclusive agreements, and at least for government contracts. That's primarily where Lockheed's sitting on that space.
Yeah, so with MITRE, we like to partner with people to co-develop IP. We do some work internally, but as this partnership with UMD, and which has been really fruitful, we generate that together, and we try to work together to make sure that IP can be, used by a future company to bring that to reality. And so I think as we talk about collaborating, we also need to talk about how to collaborate effectively with IP, and it's something that we're trying to work through.
Thank you for that plug, by the way. And Denise?
So IP is important to us all. It's something that we focus on, particularly around our hardware, as well as the software we're developing. Obviously, when you get into a customer engagement, IP is something that you have to negotiate. But I would say that, in general, I think IP is a good thing.
So would your lawyers, right?
What?
So would your lawyer.
So would our lawyer or lawyers.
Yeah, exactly.
Yes, exactly.
So unless there's a question from the audience, I just want to ask, what haven't we covered in the last 40 minutes? Are there any other near-term applications or really anything else that we want to check in about?
I'd say with near-term applications, like DoD is very interested in sensing, like I said, with the clocking, position navigation, timing, as well as magnetometry. There's a lot of really interesting applications on the horizon there. We kind of talked about this quite a bit, and then that's really the kind of main focus, at least from our perspective.
Yeah, I think for quantum sensing, areas that maybe haven't been emphasized that much are really new metrology tools for other fields outside of physicists and material scientists. So think of like the life sciences. Again, I'll go back to Envision, and the previous panel mentioned this sort of measuring the heart signals with a magnetometer. I think, that's a big area. There's a lot of excitement there, and it's sort of on us to say what capabilities can we provide there, and potentially there's bigger markets there.
So application, well, I do want to mention, I think all the startups in Traction had some very interesting offerings. So I think, and Andre talked about a lot of the different companies in the industry. So there's still a lot to come, and there's still a lot of innovation and imagination that's going to come. And I think part of the fun of all of us in the room is that we're here early and we get to watch this unfold and see those surprises along the way. And I think there will be more surprises.
I definitely think so. Having worked in academia for a while now, and now with the Quantum Technology Center, seeing a lot of very, very interesting things coming out of academic labs, where essentially you get something at a TRL of 0, and then moving all the way up to 3, 4, and then turn into a spin-out company. So I think, from my perspective, I think academia is kind of where the next wave of quantum is going to come out. And we were talking about IP. I really do believe that the next wave of IP is going to be starting in academia and then going into the next generation of quantum companies. Does anybody in the audience want to add anything to? Yes, sir. Yes, please.
How far away are
Thank you.
How far away are we from meaningful revenue-generating business applications, meaning in the billions?
In the billions?
Commercial opportunities, yeah. Is that 3 years, 5 years, 10 years? Maybe IonQ?
I think that's one reason why I wanted to pursue a PhD, was to kind of answer that question. So it's a $1 million research question, or to say $1 billion research question.
It's a tough question, and I'd love to say, 3 years or 5 years, and it really depends on application development, and how we can link it to hardware, and how we can define a problem that, is small enough that we can do now. So a lot of that depends on the cleverness of whoever's doing the work. I certainly bet on IonQ. It's a fabulous team, but it's hard to predict. So I'll just say, can't tell you. Yeah, stay tuned, exactly, yeah.
I think you can kind of equate it to where we were when the transducers were first introduced in like the mid-1950s. If you were to ask that question then, maybe somebody would have said 10 plus years, but how long did it take for IBM, for instance, to become $1 billion company? And how long were computers out there before Microsoft got created, right? So I think from my perspective, having done a little bit of studying on this, it's a lot of that. Like you can't necessarily answer it yet, because you also have to see what's kind of gonna come, and how other businesses are gonna be supporting companies like IonQ. And with quantum, you're not necessarily just talking about quantum computing, you're also talking about quantum sensing, and then all the materials that are supporting quantum sensing and quantum computing. So I think if you're looking at it as an industry as a whole, it could be billions of dollars within the next 3 to 5 years. But if you're looking at it as individual companies creating revenue, it'll probably be longer, following the advent of the creation of the computer to begin with. Yes, sir. Oh, John, can you pass the microphone, please? I'm very good at telling people what to do.
A question that more related to quantum sensing. Do you think we're doing a good enough job of linking, and I'm saying we as the royal we, but by linking the problems the different industries, different subsets of these industries are facing in their day-to-day life with potential solutions in quantum sensing?
Yeah.
I think there are some examples that we're giving, right? You gave the good example that with the chip production in engineering, some magnetometry for heart monitoring. But again, there must be a plethora of problems out there that may be solved by quantum sensing, which we are not really aware of. Yeah.
Oh, yeah, I totally agree. I think that's like, in quantum sensing, that is the next 3 to 5 year challenge, is who can most effectively find those problems and then match it with the quantum sensor technology. Because I think quantum sensing has the potential to really impact society in so many different areas, and unlock new big markets. But I guess that's $1 million question. Can you find that application that's gonna
And
open you
so
up?
I'm sure we don't have to tell you, but quantum sensing, just like quantum computing, takes a lot of money in the beginning and a big investment in the beginning. And we're here at this Quantum Investment Summit, but quantum sensing in comparison to quantum computing is quite small. And I think in order to improve this market and to continue it on, there needs to be an influx into quantum sensing in the beginning, and for investors to take a real risk in the beginning related to quantum sensing to have those killer applications in the near term. And MITRE Engenuity has done a great job job with some small projects developing that, but then there's the next step. How do you get that out into the commercialization field? And so with the near-term quantum sensing applications, there needs to be an influx of private capital into the quantum sensing realm. Yeah. Do we have a...
Hi, I have a question for Denise about, I was wondering if you could speak a bit more to the Women in Quantum group that was mentioned in your bio.
Very funny, there were a lot of people calling me up and asking me for help in their careers in quantum, and I didn't know how to handle this influx. It was like 20 or 40 people a week, and ended up calling Andre up and saying, what do I do? How do I handle this? And so we formed a community, and now the community has about 9,000 people in it. We have summits where we highlight women's contributions in quantum. So it's to highlight women like Noelle, scientists, senior scientists, business people, and try to give women, help them develop business skills, help them develop a network, help them with mentoring so that they can move on to the next stage of their career.
And I will put a plug in for somebody like myself who is not a quantum physicist, but more quantum curious, as David explains, and there's opportunities on the business side that are up and coming, and I think that's really where women can contribute to as well. Not to say that women could not be forefront as physicists, but for those who are a little bit more behind the scenes. And with that, I will get off my soapbox and thank our panelists for our wonderful panel today. And thank you for an audience, thank you for the wonderful questions. And now you can all have lunch.
All right, so with that, I would like to thank all of our speakers and our panelists this morning. I heard some great challenges to the entrepreneurs to come up with those clever billion-dollar ideas. I heard some great challenges to our investors to make sure that we actually have the capital to be able to deliver on all of this vision. And thank you to President Pines for really believing in quantum and providing all of the support that we need. So we'll be taking a quick break, so please be sure to come back at 12:15. We'll have a fireside chat with our keynote speaker, Peter Chapman from IonQ. So we will see you very shortly. Thank you.